This is going to be our review session for exam 3. That's going to cover chapter 5 and 6 for Chem 110. So this is going to be review for exam 3. This is going to cover chapter 5 and 6. One of the questions would be simple application of this expression. Delta E, change in internal energy, is given by Q plus W. This is the amount of heat added, and this W is work done on the gas. Done on the gas. But if it is work done by the gas, then there will be negative sign in front of it. So that will be negative. So there will be a simple application of this expression, which is based on conservation of energy. Then I'll ask you problems on applications of methods, which gives you heat of reaction or how much energy is given off in a chemical reaction. So this includes calorimetry, which is a straightforward heat calculation. So heat would be given by mass times specific heat times temperature difference. So if you, this is mass, this is specific heat, this is temperature difference. So if you multiply these three numbers, you're going to get heat. So that could be a simple problem on these, in which mass would be given, specific heat would be given, or temperature difference would be given. Sometimes I give you initial temperature. From temperature difference you can get the final temperature. So if I give you initial temperature and quantity of heat, so first you calculate delta T, which is temperature difference, and then by knowing whether that final temperature is going to be higher or lower, accordingly you find out the final temperature. Then I'll be giving you a series of reactions, and you need to identify the reaction that gives you heat of formation reaction. For example, if I give you these two reactions, ammonia gas plus HCl, giving ammonium chloride, which is a solid, or aqueous, it doesn't matter, let's make it, if it's an aqueous solution, we can have aqueous AQ, or otherwise we can just have solid there. Or I can have nitrogen plus hydrogen plus chlorine, these are gases, giving NH4Cl solid. I like to keep this one fixed, so not changing here. I must have half moles of Cl2, 2 moles of H2 to balance it, and half mole of N2Cl. If I give you these two reactions and delta H values, say delta H values are given for both, then you need to identify which of these two reactions gives you heat of formation, because heat of formation is a specific kind of heat of reaction given by the reactants which are in elemental forms. So like in this particular case, ammonium chloride is given by nitrogen, hydrogen, Cl2. These are pure elements. And this is the reaction that gives you heat of formation. So all the listing of heat of formation values, the standard heat of formation means under standard state, like under 1 atmospheric pressure, most stable form of these substances, and at 25 degrees centigrade or 298 Kelvin. So this is the reaction which would give reaction for heat of formation for ammonium chloride. So keep that in mind. Even though this is also a right reaction that gives the ammonium chloride, but this doesn't give heat of formation. So in order to get heat of formation, you have to pay attention to the fact what makes that compound. The reactants will have to be in the form of elements under standard state. Under standard state, nitrogen is not N, it's N2, hydrogen H2, Cl2. So if you look at the definition again, you'd find out that it's the heat of reaction involving formation of 1 mole of a compound from its constituent element. These are the constituent elements under standard state. So that only identifies this equation to be the heat of formation reaction. So the value that we get for this would be heat of formation for ammonium chloride. Now keep something in mind, for pure elements, heat of formation is 0, so let me just show you some of these values. For O2 gas, it's a pure form of element, is 0. So in exam, it would save your time if you know that for pure elements, heat of formation is 0. So hydrogen, nitrogen, oxygen, I mean, they all have heat of formation value of 0. The next type of question would be heat calculation from mass of reactants, mass of products, or heat values. So this is the heat of reaction from mass or given heat. Or heat value. I can best explain this by going over a problem. This is the problem from chapter 5. So 5.43 is the problem. This is the reaction given, 2Mg plus O2, that gives 2MgO, and that change in enthalpy value or heat value is minus 1204. That's kilojoule. Okay, now in this problem they're saying that, I think there are several different parts to this problem. In problem part C, they give you, let's do part C, minus 234 kilojoule. What they're saying is, in this reaction, when you get 234 kilojoule of energy given off instead of 1204 kilojoule, how much of magnesium oxide is formed? Okay, so we're going to find from here 2 gram of MgO. I can ask you this question in several different ways. I can give you certain grams of Mg and ask you, if I have 5.0 gram of Mg in this reaction, how much energy it's going to give you. Or I can tell you that, like in this particular problem, 234 kilojoule of energy is given off, for which is negative, and how many grams of MgO is formed in this reaction. So let me show you how to do this problem. Start with minus 234, which is given, kilojoule, times, always try to use the known information. Known information is minus 1204. Minus 1204 kilojoule. Now question is asking about MgO. We get this much of energy when 2 moles of MgO is formed. 2 moles MgO. So let me make it clear. This amount of energy goes with 2 moles of MgO, 1 mole of oxygen, and 2 moles of magnesium. It's just in this problem they're asking about MgO. That's why I'm writing down MgO on the top. So kilojoule would cancel out. That would give me mole of MgO. Now from mole of MgO I can get gram of MgO. 1 mole MgO has 40.305 gram MgO. By looking at periodic table and adding up all the masses, I got these values. So final value is 15.7 gram MgO. This is the typical problem in which one of these values would be given, could be mass in gram of Mg, mass in gram of oxygen, MgO, or the heat value be given. So based on that, you can calculate any reactant or any product that's going to be associated with the value given. In this case, the value given is 234 kilojoule of energy given off. I have assigned a number of problems. Make sure you do those problems for a practice. Next type of problem would be application of Hess's law for heat of reaction calculation. Heat of reaction calculation from Hess's law. Again, I'm picking this particular problem from the book, but there are many other problems. So this is chapter 5, this is number 65. H2 gas plus F2 giving 2HF gas, and delta H value for this reaction is minus 537 kilojoule. Let's call it reaction 1. Reaction 2 is carbon solid plus 2F2 gas, that's giving CF4 gas, and delta H for this reaction is minus 680 kilojoule. And third given reaction is 2 carbon solid plus 2H2 gas, that's giving C2H4 gas, and delta H value for this is plus 52.3 kilojoule. Based on these three given reactions, you are supposed to calculate heat of reaction for the fourth reaction, C2H4 plus 6F2 gas, giving 2CF4 gas plus 4HF, and we need to get delta H value. That's Hess's law. Series of reactions are given and the delta H values are given. Based on that, you calculate an unknown reaction, but they're related to these three. So we're going to show you how to solve this problem. This is a very important problem, and there are several other problems that I have assigned. So make sure you first understand how I did this. You can do this problem in more than one way. The way I think could be easiest is the way I'm going to show you. Now first look for something unique in reaction 1 that doesn't appear in reaction 2 or 3. Now I can see here HF doesn't appear in other reactions, second or third. These are three given reactions. So let me write down here, this is the given. And this is the unknown. That is what we need to finally get. So you'd be only looking at the given reactions. What is unique? Let's highlight that. HF is unique. That doesn't appear in reaction 2 or 3. Now, if I know that this is unique, now focus on HF in final reaction that you end up with. This is the final reaction where HF is on the right side. So that means I don't need to switch the reaction. Keep the reaction as it is, only you need to multiply the reaction by 2 so that you get 4 here. This is 2HF because you want to get to this. So you need to have 4HF. In order to get 4HF, you need to multiply the whole thing by 2. Well, let's do that. 2H2, 2F2, this is changed to 4 now because I multiplied by 2. And don't forget that you need to multiply delta H value also by 2. Now keep in mind that why I did that, because in this reaction we had 2HF, but in my final reaction that I'm supposed to get, I have 4. So that's why we had to multiply by 2. Now let's come to the second given reaction. What is unique? Right away I can see CF4 is the unique. That doesn't appear in 1 or 3. Now you focus on the unknown reaction. This is the one. It's on the right side. So that means I don't need to switch this reaction. Only thing is I need to multiply by 2 because this needs to have 2. Okay, so this multiply by 2, 2, and then this 2 becomes 4, then this becomes 2, and this number is also going to be multiplied by 2. Now let's get to the third reaction. What is unique in third reaction that doesn't appear in 1 or 2? C2H4. So that's unique. In my target reaction or unknown reaction, C2H4 is on the left side. So what I need to do is switch the reaction. So the C2H4 goes to the left side. So when you do that, let's do that. C2H4. Before I delete that reaction, next reaction, I'm going to copy everything. 2CS plus 2H2 gas. When you switch a reaction, delta H magnitude remains the same, but the sign gets changed. 52.3 kilojoule because you switch the reaction. So let's double check this and then you can delete the top reaction. So I'm going to delete that C2H4, C2H4, 2C. Okay, now I'm going to delete this. So this is the switched reaction. Just to remind you, I'm writing down here, it's the switched reaction, and that changes the sign of delta H. Now, C2H4 has 1, and this also has 1. That means I don't need to multiply this by any number. Right now, we're in right shape, so just add these 3 reactions, just like you'll be adding in any algebra. This is like equal sign, arrow is like equal sign, add them up, and you'll find that you're going to get this. Rest would cancel out. I'm going to show you how you cancel out. I'm going to show you one of them. 2 carbon on the left side cancels out with 2 carbon on the right side. In the same way, you'd find that everything would cancel out except these. And that would give you the final answer, and add up all the delta H values, and that gives you 2488 minus. I'm sorry, minus 2486.3 kilojoule. So that's the final answer. I have assigned several other problems, and most problems would work out this way. That means you look for something unique and then find out what you need to switch a reaction or not, then multiply if there's a need for that, and then finally you add up. Okay, next type of problem is coming from chapter 6. A simple application of C equals to lambda times frequency. This is velocity of light. which is fixed, 3.00 times 10 to the power 8 meter per second. This is the wavelength. This is the wavelength. If this is radiation, you're looking at the length between these two is a wavelength, or between these two. That's wavelength, and this gives the frequency. That means how many such wavelengths are passing every second. So that would be a simple application of this equation, and I may ask you to calculate lambda, or wavelength, or frequency, then the other values will be given. So that should be pretty straightforward. But make sure you pay attention to the units. Next, I would ask you a question on electron transition. And whether energy is given off or energy is absorbed. So if it's Ni, initial N value, is greater than Nf, or initial value is less than Nf, what happens to energy? Let me show you a simple diagram. So this is N equals to 1, this is N equals to 2, N equals to 3, and these are all these orbits for electrons to move around. Say electron initially here, it is jumping to here. So in that case, Ni equals to 1 and F for final is 3. It's like you're going from first floor to the third floor. You need to put some energy, otherwise you can't go up. Same is the case with electron. It needs energy, so it needs to absorb energy in order to go from level 1 to level 3. So when I give you this information, Ni greater than Nf, electron transition would need energy. So that would be absorption of energy. If the reverse thing happens, if I say Ni equals to 3, Nf equals to 1, that means initially electron is sitting here, finally is going back to 1. That means initially I have more energy, finally I have less energy. Extra energy is given off. So this is given off. In this case, absorbed. So there will be some simple cases given where energy is absorbed and one is given off. So I'm just going to test whether you understand the basics of electron transition or not. Then there will be a question on matter wave. These problems are also very straightforward, but you have to pay attention to the unit because a lot of times students make mistakes by not looking at the units. Lambda equals to h over mu. So I'm going to write down what units are expected. Math has to be in kilogram. This has to be meter per second. And then this is 6.63 times 10 to the negative 34 joule times second. And 1 joule is 1 kilogram meter square per second square. So keep these in mind when you do this problem. So it'll be a pretty straightforward problem. If I give you mass in gram, then you have to change it to kilogram. If velocity is given in any unit other than meter per second, you have to change it to meter per second before you plug in here. This tells you basically when there's somebody, say a jogger is moving at a particular speed, what would be the wavelength? That would be given by this. The mass of the jogger would be here, this is the velocity, and this is a constant. So try a couple of problems so that you get used to this. Next type of problem would be valid quantum numbers for electrons in an atom. So there's a valid quantum numbers. I'll give you a series of quantum numbers and ask you whether they're right or wrong. So I'm going to show you a few examples because a lot of students make mistakes in this kind of problems. say I have 3p subshell. What would be the N, L, and ML values associated with 3p subshell? This 3 is N value. So N value is going to be 3. That means in the third floor or third major level, you have subshell P. So subshell P belongs to the major level 3. So N equals to 3 and L is equals to 1. Now let me remind you how this works. In case you forgot, L, 0 stands for S, 1 for P, 2 for D, and 3 for F. So you'll have to know that 0S, L 0S, 1P, 2D, 3F. So now I have P subshell, so it has to be L equals to 1. Now I want to remind you that for N equals to 3, L values, possible L values could be only 0, 1, and 2. And this is 1 in this case because it's P. ML values, when L equals to 1, ranges from minus L to plus L with an increment of 1. So this would be minus 1, the minus of this value, 0, plus 1. And each represent one orbital. So that means 3p subshell has 3 orbitals. And those 3 orbitals are represented by ML value of minus 1, 0, and 1. Now, in exam, if I give you a question like this, that I have 3p subshell and it has N equals to 3, L equals to 1, and ML equals to 2. Right away you'd say it's wrong because ML cannot be 2 when L equals to 1. It can be minus 1, 0, or plus 1. So basically by giving you this kind of question, I'll be testing whether you understand the NL, ML, and MS values and which ones are the valid set of numbers. Let's try one more example. This time, rather than identifying F or P, I'm going to write down these values and see whether you can understand whether it's right or wrong. N equals to 3, L equals to 3, ML equals to 0. The question is, are these 3 numbers valid? Let me remind you, N equals to 3, you know that these are all major levels. You have central nucleus and level 1, level 2, level 3 are principal level. These are the 1, 2, 3. So it's the third principal level. This represents a sublevel within that principal level. And this represents a particular orbital within this subshell or sublevel. Now whether these 3 sets of numbers are right or wrong, let's examine that. For N equal to 3, the valid L values are 0, 1, and 2. It has to begin with 0, and it would be L minus 1 with the last number. So 0, 1, and 2 are the valid set of numbers, so 3 is not a valid number. So that's wrong. So read this carefully and make sure you come up with the right answer. Okay, let's try another one. 5s, 3f, 5f. Are these valid sets of representations? Let's try that. 5s, n equals to 5. There's nothing wrong with having s. This is how it goes. For n equals to 1, we'd have 1 subshell, 2 would have 2 subshells, 3 would have 3 subshells. This is how it goes. If I have n equals to 2, I'd have 2 subshells, s and p. N equals to 3, I would have 3 subshells, 1, 2, 3. But the values would be 0, 1, and 2. n equals to 4 would have 4 subshell, but that subshell would have this, and this, or in terms of L values, it would be 0, 1, 2, 3. So always you begin with 0 and stop at n minus 1. So in this case, the valid L values would be 0, 1, 2, 3, and 4. So L equals to 0 would make S. So this is okay, nothing wrong. Let's now examine 3F. Here n equals to 3. The valid numbers for L, 0, 1, and 2. Remember I said it would be n value minus 1 where you stop. These are the 3 possible subshells. Or you can write down S, P, D. That means it could be 3S, 3P, 3D. But 3F is not allowed. So that's wrong. So you cross out. Now let's examine 5F. N equals to 5. Just a few minutes ago we talked about this, but now we're talking about 5F. L can have values 0, 1, 2, 3, 4. Because I would have 5 of them, 1, 2, 3, 4, 5. So since you start with 0, you end up with this number minus 1. So these are the subshells. This is S, P, D, F. You don't need to know beyond this, but if you want to know, it's G. So F is a valid number, so 5F is fine. Okay, so this is how you can find out which ones are valid subshell representation and which are not valid subshell. So I'll be testing you with this kind of problems. Next, I'll give you electron configurations and ask you whether they are acceptable or not based on Pauli exclusion principle. So let's call it 9F. In your study guide also I have given you this kind of problem. So this explains this is 1s, this is 2s, this is 2p. These are the 3 orbitals for 2p. Question is, does this violate Pauli exclusion principle? Let's examine that. What Pauli exclusion principle tells us is no 2 electrons. Let me write down what is Pauli principle. No 2 electrons in an atom can have same N, L, ML, MS values. So that's what we know from Pauli exclusion principle. No 2 electrons in an atom can have the same N, L, ML, and MS values. Let's now see whether this is valid according to Pauli exclusion principle. This has N equals to 1. First electron has N equals to 1. Second electron has N equals to 2. So it's fine. Up to this is fine. Now let's go for the next one. N equals to 2. That's also same here. But look at the L value. Since this is 2p, there are 3 L values. 0, 0 and 1, I'm sorry, there are 2 values. 0 and 1, this is S and P, that's 2p. So this would have L equals to 1, and in this particular case, I have L equals to 1, because that's 2p we're looking at. So this is 2p, what you're looking at now. Now, ML values for these 3 electrons, we're focusing on this, must have 3 different ML values. Each would represent 1 orbital. So minus 1 for one, 0 for the other one, plus 1 is for the other one. So in other words, this particular electron has N equals to 1, and it's the same kind of spin, but look at the second one, doesn't have the same. So I don't have any problem with Pauli exclusion principle here. no two electrons in this case has the same value of NL, ML, or MS. MS value is the same for each case. This is electron moving in one direction, spinning in one direction. So it could be either plus 1/2 or minus 1/2. Let me repeat this in case you didn't quite get it. No two electrons in this electron configuration has the same NL, ML, and MS values. MS values are all same for all these 5 electrons. But what is not same is N value for these 2 electrons. N values are different. For the second and third, N values are the same, but L values are different. Because this is L equals to 0. 2s means L equals to 0. And these L values are -1, 0, +1. So as you can see, that no two electrons have the same N, L, ML, or MS values are same in both cases. So pay extra attention to this kind of problem. Now, let's change this question so that we understand better. So let's now change it. Instead of having 1 electron here, let's move it in here. Is this going to violate Pauli exclusion principle? Look at here more closely. These 2 electrons, n equals to 1. Both of these electrons are in the same orbital, so n equals to 1. Now, L value for both electrons is 0. So both 1 and 2 electrons have n equals to 1, L equals to 0. ML also equals to 0 because they have the same, they're in the same orbital. MS is also same, it's spinning up, either +1/2 or -1/2. That means these 2 electrons have same set of 4 quantum numbers, and for which this is not valid. So according to Pauli exclusion principle, you cannot write down like this. Rather, you'll have to move one of these electrons, either pair it up like this, or move it up to another level. When you pair it up, one of them would have MS equals to +1/2, the other one would have -1/2. Then it would be all right. So read this carefully about the application of Pauli exclusion principle. Then there will be a question on electron configuration. By looking at periodic table. Say I'm looking at zirconium. You should have a periodic table in front of you because that would help you. The first line would have 1s2. Second line you begin with 2, 2s2. And on the far right, you'd have P1, P2, P3, P4, P6. So go all the way to the end. In the same way, the third line, you have 3s2, 3p6 on the far right. Then you have 4s2, is the fourth line in periodic table. And then you come to the transition element, which has line number -1. Fourth line, so line number -1 is 3, 3d. And you fill it with all 10 electrons. Then 4p6 far right, 5s2, and then 4d. Again, you come to the transition element, so line number -1, that gives you 4d, and 2, and that gives you zirconium. So you should try working on one of these problems. Sometimes I give electron configuration and you need to find element. So either way, you'll be able to get the right answer if you know how to use periodic table to get the answer. Sometimes I ask for unpaired electrons. I think I forgot to give this. This is a G. number of unpaired electrons in an atom. Let's apply this. Whenever you fill in all these subshells and orbitals, you see that they be all filled in, then you go to the next level, then next level, next level. So mostly unpaired electrons would be in outermost orbitals. So you need to examine the outermost orbitals for ground state electron configuration. Ground state means normally what you expect. So this is the ground state. Now 5s is completely filled, so let's still write down so that we all understand. This is 2 electrons in 5s, up arrow and down arrow, and then 4d. Remember, d has L equals to 2. So when you have L equals to 2, we have 5 orbitals. So number of orbitals equals to 2 times L plus 1. So that's 2 times 2 plus 1. So that's 5. And that's why it gets 5 orbitals here. 2, 3, 1, 2, 3, 4, 5. Or you can write down in terms of ml values. ml is minus 2, minus 1, 0, plus 1, plus 2. That's 5. Now there are only 2 electrons. According to Hund's rule, you have orbitals like this with same energy. Electrons would fill them singly before they start pairing up. So in other words, in this case I have 2 unpaired electrons. Okay, so that would be a question on number of unpaired electrons in an atom. So far we talked about ground state electron configuration. Ground state means normally at room temperature. Let's now talk about excited state electron configuration. Excited state electron configuration. I'll give you something like this. I think I got this from chapter 6, number 74A. 1s2, 2s2, 3p2, 4p1. That's given. How do I know this is an excited state electron configuration? Think about how many electrons you have. 2, 4, 6, 7. 7 electrons. Normally, this is how electrons gets filled in. 1s, and then you go to 2s, then 2p, then 3s, and that's how it goes. For 7, the first 2 go in here, second 2 going in here. After it's completely filled, it goes to the next one. The 4, and 2p3. And these are all empty, and we don't show the empty ones. Since there is no electron in 2p, that means it went out of 2p to 3p and 4p. And that's why this is an excited state. That means normally you would not expect this electron configuration. This is the ground state for this electron configuration. So how do I get the ground state? First, calculate the number of electrons, 2, 4, 6, 7, and 7, and then assign the electrons by looking at periodic table, which would give you the normal subshells sequence, 1s, 2s, 2p. And this is the sequence of subshells according to energy. And then you can identify the element. This is nitrogen from periodic table. Okay, so the question is, if excited state electron configuration is given, how do we get ground state electron configuration, and then how do you identify the element? So this is the element, which is nitrogen. Next question is, I often consider that to be next question to be based on our general knowledge about different types of waves or radiations and their energies. So you need to know high energy radiation, high-low wavelength. For example, if you look at visible light, we often write down like this: Roy, G, BIV. Red, orange, yellow, green, blue, indigo, violet. The white light has all these components. If I ask you among these radiations or lights, which light has the maximum energy among the visible light components? In rainbow you see this light separated, and which has the least amount of energy? This has the largest amount of energy among the visible. This has the least amount of energy. Red has the least amount of energy. So high energy, low energy. Wavelength goes just the opposite way. Among these, this has the large wavelength. This has small wavelength. So you can see here, smaller is the wavelength, higher is the energy. X-ray is harmful because X-ray has a much smaller wavelength, so X-ray has a lot of damaging effect on your tissue. So too many X-rays are bad for you. But a few X-rays would be all right because our body can cope up with that. So we'll have to have that kind of understanding that among these threes of wavelengths, like not just the visible, beyond this we have X-rays, gamma rays, radio wave goes the other way, microwave, what kind of wavelength or energy do you have? You don't have to know exact number, but you need to know the relative position. That means which has more higher energy than which. For this review, the last problem would be on photoelectric effect. Einstein's photoelectric effect. The problem that I picked is number 31, chapter 6, number 31. Let me draw this so that you have an understanding. Here, electron is bound, light is shining, and that's going to eject the electron. The frequency is given 1.09 times 10 to the power 15 waves per second, or wavelengths per second. Now, the question wording could be like this. This much of frequency is needed to knock off an electron from a metal. So what is the energy needed? So basically you're going to use this formula, E equals to H times nu, and that will tell you how much energy is needed to knock off that electron. So it's pretty straightforward. If binding energy of this electron is given, say binding energy is given, then you need to do one additional step of this calculation. Let me show you how to do that. Kinetic energy of electron, this ejected electron, will be given by energy of the light photon. This is the energy of the light particle, H times nu, minus the binding energy. Just make sure you have the right units so that you can subtract and it gives you the kinetic energy of the ejected electron. So if frequency is given, I can calculate energy. If wavelength is given, I can calculate energy. But if wavelength is given, this would be your setup, hc over lambda. C is the velocity of light, and we know the value. So if this is given, this is already known, this is also known, I can find out the energy. So make sure you try working on these problems, and that will prepare you for this exam.